In this video we solve problem 8 of unit 12. The first part consists on finding the equivalent capacitance of the combination. So I'm going to first draw the combination. So we have three capacitors, A, B and C. All three of them have the same capacitance, which is 3 microfarads, and between points 1 and points 2 there is a difference of a potential difference that we normally call V, that is equal to 500 volts. So to find the equivalent capacitance, we are going to we want to go to a set in which there is only one capacitor with the equivalent capacitance that is storing the whole amount of charge, and in which the difference of potential is the same one as the one applied between points 1 and 2. This is the 500 volts. I would suggest not going directly to the final point, but looking for some intermediate point, because if you look, capacitors A and B are combined in parallel. So we could first of all draw an equivalent set in which, instead of having capacitors A and B, we have a capacitor D with a charge Q sub D that is the equivalent of the set of capacitors A and B combined in parallel. Okay, so this would still be capacitor C with its own charge. Okay, so these are points 1 and points 2. So to solve this, we look at A and B. We know that they are connected in parallel. So we, if you look at the theory, we know that the capacitance of the equivalent capacitor D is going to be equal to the addition of the capacitance of A plus the capacitance of B. Okay, so this is going to be 6 microfarads, because A and B have each 3 microfarads. On the other hand, we also know that the charge in D is going to be the addition of the charge in A plus the charge in B. Okay, so now to go from the middle plot to the final plot with the equivalent, the whole equivalent capacity, we see that capacitors D and C are arranged in series, and that means that their equivalent capacity is equal to 1 divided by capacitance of D plus 1 divided by the capacitance of C, all to the minus 1. Okay, so this is equal to 1 over 6 microfarads plus 1 over 3 microfarads to the minus 1. If you do the numbers, this gives you an equivalent capacity of 2 microfarads. Okay, so this solves the first part, and then in the second part we are asked to derive what is the charge stored in each capacitor. So we're going to look at that now. So for each capacitor we would be best going backwards. So so we have for B, we have that we could first of all know what is the charge in the equivalent capacitor, because we know that the capacity is the ratio between the difference, the charge stored in a capacitor and the difference of the potential difference across the plates. So this leaves you that the total charge in the equivalent capacitor is going to be the equivalent capacity times the difference of potential, which is 500 volts. So this is 2 microfarad times 500 volts, which provides a total of 1 microcoulomb. Okay, as capacitors C and D are both in series, and their equivalent capacitor is this one, that means that the charge in D is the same that the charge in C, and it's the same to the equivalent capacity. To the equivalent charge, which is 1.0 microcoulombs. So we already know how much charge we have stored in capacitor C. Now we have to turn our attention to the combination of capacitors A and B that gave you capacitor D. So at that point, we know that capacitor charge A plus charge B is equal to charge D. On the other hand, we know that charge A has to be equal to the capacitance A times the potential difference A, and charge B is equal to capacitance B times the difference, the potential difference across B. If you look closely, you can realize that as they are A and B are both in parallel, the potential difference across them is the same. This is VA and is equal to VB. It's the same potential difference. On the other hand, we also knew that capacitor A was equal to capacitor B because they were all three capacitors that had the same capacitance. So this means that the charge in A has to be equal to the charge in B. Okay, so this means that charge in D is twice the charge in A or twice the charge in B. So that means that charge in A has to be, that is equal to charge in B, has to be charge D divided by 2. This is 0.5 microcoulombs because charge in D, if you remember, was 1 microcoulomb. As for C, they ask us to solve the potential difference across the plates of each capacitor. And that, with all the data we already have, is quite easy because we know that the capacitance is equal to the charge divided by V. So V is equal to the charge divided by the capacitance. So we can apply this to each capacitor. So we will have that capacitor A has a difference of potential difference across plates that is equal to charge A divided by capacitance A. And this is equal to 0.5 microcoulomb divided by 0.5 millicoulomb divided by 3 microfarad, which is 167 volts. The same goes for B. If you do the same calculation as the numbers are the same, this gives you also 167 volts. And for capacitor C, this is going to be charge in C divided by the capacitance of C, which is just twice that, 333 volts. The last part, they're asking us to solve for the energy stored in the whole set, and that is quite easy because we can go directly to the capacitance and to the capacitor that is the equivalent, because there we know that the energy stored in a capacitor is going to be 1/2 times the charge that is stored times the differential of the potential difference across plates. So we can apply this directly to the equivalent of the set, and this gives you 0.25 joules. You can also see, I leave you to calculate it, that the total energy stored in the system that we've calculated very easily as this is equal to the addition of what is stored in capacitor A plus what is stored in capacitor B plus what is stored in capacitor C. And each of them, you apply the same expression. In A, for instance, has the energy stored has to be a 1/2 of the charge in A times the difference, the potential difference over A. That is, in this case, 0.04175 joules. If you do the same for B, that is going to have just exactly the same amount of energy stored, and you do the calculation for C and you add them all, you come back to the same expression.